let me use the time to introduce our keynote speaker of today, and also the final keynote speaker of this meeting. And it's a great pleasure for me to have one of the eminent figures of different aspects of our Atomtronics meeting, and I'm going to tell you what I mean by that. But let me introduce Professor José Ignacio Latorre, who is the chief researcher of the Quantum Research Center and with that the Technology Innovation Institute in Abu Dhabi. And José Ignacio, he started his work in high energy physics in Barcelona, and then he switched to solid state physics. And then, of course, he's very, very famous for switching again and starting the field of quantum information, where he, of course, is one of the eminent figures to start this, this work. He was doing Fulbright fellowships in Boston and MIT, and he was going to the Niels Bohr Institute in Copenhagen, and then he turned back to become a full professor in theoretical physics at the University of Barcelona. But at the same time, he was doing extensive research stays at CQT, the Center of Quantum Technology in Singapore, at CERN, and in Amsterdam and MIT again. And now he's on leave from Barcelona, as far as I understand, and he's the chief researcher of the Quantum Center in Abu Dhabi. And he's promoting cutting edge research in quantum technology. And he's promoting the idea of building a quantum computer in the Middle East, and also of developing a new generation of quantum technology in the Emirates. He's connected to our meeting in another way because he's the founder of the Center de Ciencias Benasque Pedro Pascal, which is, of course, the home place where we have our meetings usually. So we're very happy that you stepped in and now give us a host institution for this year's meeting. He's also, as you can see, very much involved in outreach. So he made two documentaries, and one, of course, on Glauber, which we, of course, love, and he's one of the famous figures in quantum optics. And finally, I would like to mention that on top of all this academic revolutions and all his academic achievements, he's also founder of several spin-off companies, and one which might be one of the most famous one is Kilimanjaro, a company which is trying to promote quantum technology and quantum information processing. And I think I have to stop because we're running out of time if I continue to do all these ideas and all the main contributions you did to our field. And we are very thankful to you to promoting Atomtronics in such a strong way you did. And it's a great pleasure for me to give you the final stage for this meeting as a keynote speaker. And I open the stage for you on your contribution, No Hype Quantum Computing. José Ignacio, please go ahead. Contribution.
Thank you very much, Gerhard. Well, what a kind introduction. So yeah, I'm very happy to have help for the first meeting of Atomtronics in Benasque, and it was so clear to me that this was a very nice field in the beginning that I tried to help as much as possible, and as you can see, also now in the Middle East. You may wonder what a crazy title to say no quantum, no hype quantum computing. And this is in part related because I guess many of us who are now working on quantum computation, we are systematically asked questions from the innovation sector and from the venture capital about what are the possibilities of quantum computing, but they're actually pushing us to say things that are not accurate or faithful. And I'm simply having my own campaign against this quantum hype. I actually use a word which is counter hype. So it's perfectly compatible that we are making amazing progress with the fact that we still don't have dramatic results in quantum computation apart from Shor's algorithm and Grover's algorithm and a few other algorithms that have been developed. So this is a confession of humbleness, and from now on, please be patient. So the idea is clear. We had the gate secrets algorithms, but there are very few of them which are very solid. This is probably unsure. We have annealing, we have adiabatic evolution, for instance, and we can address problems, but we have very few theorems of what is the advantage you may find in an annealer, and you may be aware of the discussion earlier in the year about certain annealers not being able to deal with the sign problem, and therefore being classically simulable, okay? So one has to be very careful. And then the idea of variational algorithms, in particular autoencoders, eigensolvers, classifiers. So first I will try to say something about the later. So variational quantum circuits in a way inherit a lot of ideas from artificial intelligence. So the idea is how to make a quantum circuit that can do a task, but that's very similar to what is the way to make a neural network to learn a task. So you may think that there are two different machines, a classical machine and a quantum machine, but the procedure is similar, learning. And that's why we inherit supervised learning and supervised learning, reinforcement learning. We may go beyond to Q-learning, convolutional neural networks, adversarial neural networks. And we should reproduce certain theorems that you have in neural networks, like the universal approximate or relation to Gaussian processes. So there is a lot to be learned from artificial intelligence. The rationale for these variational quantum circuits, for me, it's very clear. So the idea is that we do have a circuit made of gates. Those gates are made out of the basis for gates. And we try to bring a given state to the state that is solving a certain problem. It might be the ground state of a Hamiltonian. It might be the codification of a solution for a three-stat problem. So in a way, let me think of the hyperspace, and we want to find a path that connects my first state to some state, which is, if not the solution, near the solution, is near optimal. So can we do that? Well, definitely, if we do have a lot of freedom of what are the gates we have here, are enough depth, it seems intuitive that we can find such a secret that achieves the purpose of going over there. Well, to be precise, we do have a theorem. This is the Solovy-Kitaya theorem that says that given a set of unitaries, which is dense, then these unitaries can form a secret, let me say from U1 to UK, that can approximate a given unitary V to a given precision. You need the definition of what distance you use here, but that's irrelevant. What is relevant is that the number of gates which are needed only scale as the log of the precision, of the inverse of the precision. So, and the coefficient is of the order of magnitude of 4, or the exponent, sorry, here. So that means that we do have the guarantee that such a secret exists and necessarily is not too large, okay? Well, of course, there is a trap here, which is to find it. The process of finding the secret may be extremely lengthy. We may need a learning time that is exponentially large. But it's a fact that we are supported by a theorem. So this makes sense. So in particular, that was proposed but in the group of Aspuro and Alan and IBM and Zapata and Blatt, the idea that you could address as a readout some properties of a molecule. And indeed, it was the energy as a function of the distance between the particles and of the hydrogens in this case, and indeed a minimum was found. There is a lot to be said about these papers because I think it's, again, a little bit of hype, but indeed it was a remarkable fit that triggered a lot of research. Now, there are so many unexplored options here. How do you encode data on these secrets, variational secrets? How do you process them? What is the architecture? How do you make the readout? Is it the same as state discrimination? Can we inherit the theorems of the 60s? Well, one of the main ways of proceeding is that in a blind way, we combine single qubit gates with entangling gates. We call that a layer. And then we may need several layers. So here is a scheme where we can learn, on the alphas to get a task done. So alphas are adjusted by a learning procedure. But how many of these layers do we need? So in a paper we produce in 19 with Carlos, Bravo Nieto, Lumbreras, and Tagliacozzo, we found something that I think is very beautiful. On the horizontal axis, you have the precision. So the further to the right, the more precise. That would be a precision of 10 to the 10 in the energy of the Ising model at the critical point. On the vertical line, you see how many layers I'm using to find this result. And what we see is that as you start to increase the size, I go from 6 to 16 qubits, you don't gain precision in the ground state. You keep adding layers almost to no increase in the accuracy, till the point that suddenly you go exponentially fast to a very precise result. So what you see here is that first you need to generate the correlations in the system, and then you refine them. And this scheme is systematically obtained. And we have obtained the very, very same scheme in a recent work with Luigi. He's the main. Luigi, I didn't say thank you for this fantastic meeting, but I take advantage. So this is a really nice meeting, and that was a result that I think is very clear of what's going on. Okay, these circuits first developed entropy, they entangle the system, and then they refine the description of the system. This said, can we apply any of these techniques to a practical problem? So we did that with a classification. You see, now you have a data. You think that you will put it in some way. For instance, let me say in 1 qubit, I make a gate that incorporates the data. And then I read out and I try to make a classification. I can even process further that qubit. If you do that, and you take a very simple problem like classifying a circle inside a square, you see it is useless. It doesn't work at all. Still, if you now add 2 gates, you make the data into, and you make an entangling gate, and you do a simple gate, then suddenly the classification goes up to a 96%. So you start to see several things here. Maybe it's that I'm adding the data twice. Maybe it's that I have entanglement. How does it work exactly? So to be a more refined analysis on that, what we argue is the following. Do the classification task on a neural network. You enter, for instance, the points of the circle X and Y on 2 neurons. Then you have a hidden layer, and then you get the final result. It works very well, a neural network. But come on, this is unfair because the data have been entered 4 times in my neural network. This is what Leandro called query complexity. The query complexity is 4 here. Okay, you have done it 4 times. So why don't we do the same with our qubits? So why don't we try strategies where we re-upload the data? Just like here, the external data are uploaded several times. We call that re-uploading technique. And for 1 qubit, the idea is that you re-enter the data, which are X, and you leave alphas as free parameters. And you can see immediately that the convergence is amazing. So this is the classification of one circle. So X and Y are entered here, and you decide finally whether it's inside the circle or outside, and you train by supervised learning. And it's amazing. The convergence is amazing. The same for any other topology. We have tried classifying different data. It is more subtle because you have to enter part of the data in each gate, yet it works fantastically well. So you see, single qubit does a task. such as classifying the points on a non-trivial topology. Can you try even non-connected pieces? Well, this is, for instance, the classification of an annulus, and this is the final result. Green is success, red on the right is mistaken. So this is really amazing. It's working. 6 layers of a quantum circuit on 1 qubit are as powerful as 100 hidden neural network neurons. So is this for just theoretical? Well, I'm very, very happy that I convinced in Singapore some of my friends to do the experiment. And these are the results of an ion trap with 4 layers. And then you can see this is a classification of a non-convex figure and a non-topologically not simply connected figure. And it's really remarkable. Actually, we can now compare even neural networks to the quantum processing unit. And it's still a little bit erratic, but the errors on the ion are really, really controlled. And we get classifications in some cases of 96%, exactly the same as a neural network. And this is an experimental result. It's not a theoretical result. This is a fully controlled ion. This is, we are now writing this with Mukherjee, who is the experimenter behind all this. So data re-uploading is query complexity, and it is the key to have these successful classifiers. Now, there must be something behind. This cannot be an accident. So then we try to understand whether there is an equivalent theorem to what is called a universal approximant. Indeed, can we prove that the 1 qubit is tantamount to create any function, whatever function, complex function? If we can do that, we make connection because the Fourier series is a universal approximant to any function. And it is, remember the theorem of for Fourier, it's a point by point. It's the most powerful way you can go to an approximant. Let me prove it. Indeed, we can make a circuit U made of a product of unitaries that I can choose to be rotations in Z, Y, Z, Z, Y. There are many options to do that. I've chosen these because then it turns out that I can make all these gates into a very simple combination of A's and B's where they are defined through the angles, okay? So that gate is represented by this unitary. And then I can proceed by induction, and I can see that if I add from n gates to n plus 1, I recover the very same expansion where the coefficients simply are found in a particular way. So you see, every time we add a single gate to a qubit, is like adding terms of the Fourier expansion that can describe any functionality. And this is a theorem. So this is proven. This is proving that a single qubit is a universal approximant to any function. It is in equal terms with a neural network of a hidden layer of the same amount of neurons as gates are in the quantum circuit. And again, we have done the experiment. This is done with superconducting currents in the hands of the experiment by Von Diaz. And here you have the comparison of the theory, which is the black, with a circuit of 2 layers on 4 layers. And as you can see, it's not as precise as the ion trap, but it is a fact that, that these circuits are universal approximants. So I would like to re-emphasize that we have a theorem. We are now missing many other theorems that you have in artificial intelligence. So this is my way of understanding that we have to proceed little by little, but with solid steps. We have to understand what is a quantum computer. Now, neural networks and quantum circuits are much better than a Fourier series. Remember, because a Fourier series, the frequencies are multiples of a given frequency. Whereas in both cases, neural network and quantum circuits, you have adaptive Fourier series. The frequencies are adapted. And that produces a gain of the naive Fourier series. So this is again why, we were having fantastic classifiers of non-trivial topologies with only 4, 6 gates. So the idea is that we are not only we can prove that at least is a Fourier expansion, but we are better than a Fourier expansion. What is the difference between a neural network and a single qubit? Well, that the neural network, the nonlinearity of the addition of the combinations of the queries is done by hand as a sigmoid function, as a cosine function. Whereas in the quantum world, the nonlinearity is done by nature itself. With the unitary evolution is an exponential, which is nonlinear, and that is done automatically. So it even means something that even if we have the same power as a classical machine, we may in the long term be much more efficient as far as energy is concerned, because we don't do the operations done by nature. So what is the role of many qubits? Honestly, I don't know. I think that many qubits will enhance everything in the way that we will have a mapping of our problem in an exponentially large space, and therefore this is a feature map, and then you can have classification, which is much easier. But do we have a theorem? We don't. At least I don't know of it. Okay, there are results that go into that direction. We know that deep neural networks act as a series of symbolic processes. Actually, they act as Gaussian processes that connect layers with layers. It is still to be understood, I think, what is the quantum circuit doing, and whether it's better or worse than a neural network. So this was my example about classifiers. And then I would like simply to give you 3 small examples of other algorithms that I think they are very nice. One is how to compute a singular value decomposition with a circuit. I remind you very briefly, any state decomposed in 2 parties, A and B, in principle has a number of degrees of freedom, which is written as a tensor with indices connected to the 2 bases. But we can diagonalize with 2 independent unitaries this tensor. Okay, that's a fact, it's a theorem. With 2 independent unitaries, you diagonalize any tensor. And this can be understood as a very clever change of basis, where now you have U and V, which are different bases for the Hilbert space A and B, but now the terms that connect them are only diagonal. That's very beautiful because that serves to compute entanglement entropy and many other properties of the system. We know how much correlation there is between Alice and Bob. Can we do that on a quantum computer? And the idea here we had was that you simply do the following. You put a unitary on Alice, a unitary on B. They never talk. But now you train the parameters in Alice and Bob so that the output is always the same. If I get 0, 0, 1, the other should be 0, 0, 1. If I get 1, 0, 0, it should be 1, 0, 0. So in a way, I'm training this to be EI, necessarily by this training. Okay, but as you see, that is a local transformation, and they are the same. So the coefficient can only be lambda I any phase times any phase, because the eigenvalues are related to entanglement, not to local unitaries. So in this way, I can read out every time I measure, I will now read the probability of lambda I. So I think it's a beautiful way of finding the eigenvalues of singular value decomposition. And we did the numerics for that. And you can even see that once you have done that, you can, you train the U and V to get the Schmidt decomposition, and then you do the opposite. And this is the same as a non-local swap without quantum communication in the swap. So there are theorems that are very beautiful that can be done like that. I would like to bring a second example of a fun algorithm we are working, and that's why I'm bringing it here, which at some point we thought of how you could codify classical data in a quantum state. Well, we all the time say that the quantum state has an exponential space. So why don't we show you use it? And the idea is whether you can map a picture into state. And let me do it in the following way. I take the pixels of a picture, and I think the first quadrant, I call that quadrant I want 1, 2, 3, 4. So my first quadrant is 1, 2, 3, or 4. If I go to another one, I have 1, 2, 3, 4, and I have a second quadrant. And then when I'm finishing, it's a gray color. So I assign as coefficient the gray color of that guy. So you see 4 to the n pixels are mapped onto n quadrants. So it's an exponential compression of classical data into all the freedom that you have in the quantum state. And then you can do things because now you have a state. You can do things. You can transmit it, you can manipulate it, you can compress it, you can do things. In this exercise, what I did was to use tensor networks to compress the state. And you can use ancillary indices. You can do product state, you can do Chi2, Chi3, Chi4. You can improve the faithfulness of the tensor network by increasing the ancillary. Well, I did that in detail with the famous picture that everybody used for benchmarking. And this you see how you can use the tensor network representation of the codification of the picture as a ket, and how it was compressed and how it gets better if I use more ancillaries. And I've given this example because this is an example of what you would call quantum inspired algorithm. It is a classical algorithm, finally. Every data is safe as a classical data. In the middle of it, I pass from the picture to the ket, and then I use tensor network to compress the ket. And this is the kind of thing that now people are doing in different fields. There are a couple of companies that I'm friends with that are doing only quantum-inspired algorithms. And we are using the same technique of compressing data in this exponential way for other problems now. My final example is about option pricing. Everybody is so excited about finances. So we did a little thing. Let me tell you what we did. I remind you of what is the problem of option pricing. You have an asset and you want to predict the value of the asset at a given future time with a probability distribution. The difficulty is that you have a piece, which is the interest rate, and that would be deterministic, but you have a stochastic variable and with a volatility. The only way people are doing now these things seriously is with the Monte Carlo simulation. So what you're doing is to compute the payoff, which is the value of the stock at time t, maturity time, given the probability of being there. And then you have to integrate that equation. You have to do the Monte Carlo. That's the idea. You reproduce the Monte Carlo, you have the distribution, and now you say, my strike price was here, then I compute my gain or my loss. So our idea is that this path looks extremely similar to a unary representation. So that you go up, you go down, just as from one qubit to the other. So that seems a little bit crazy. No? I mean, I'm trying to codify the value of the stock in a very inefficient way, because that's a unary representation of these kinds. But there are plenty of mysteries in the unary representation. There are many simplifications which are amazing. So the idea is try to make it, okay? And that's exactly what we did. We constructed a circuit that would distribute in the unary way the probability distribution to compute the expected payoff, but we also add amplitude estimation, amplitude amplification. We did that, and this is the way you distribute the probability in the unary. It's very efficient. And then we computed in a given way the payoff. So that's the way you do it. You can do it, okay? And now we apply amplitude estimation. Well, amazingly, for accuracies of less than 0.2%, you don't need many qubits. You can do it with a reduced amount of qubits. And what is better, in the unary, you save errors. Imagine you have double counting, then you discard that. That's impossible to do in the binary. In the binary, you make a mistake in the relevant digit, and the asset that was worth nothing becomes to be the most valuable. So the error you introduce in young computation is amazing. In the unary, that is very difficult because you have to lose one qubit and gain another. It's a double error to make that mistake. So by post-selection of errors, turns out that suddenly unary has an enormous potential with up to 100 qubits. Okay, we have explored that, and now we are going a little bit crazy, and we want to do this circuit in unary representation with waveguides. So with photons, single photons in a waveguide, and that's the way we generate the probability distribution. So it's the same as bosonic sampling, but instead of generating a probability distribution which is useless, which is only made for, for trying to prove a quantum advantage or supremacy, as people say, it's a useful one. So we try to substitute the Monte Carlo by a distribution of probability in unary representation. And therefore then the operations are easier and you have error correction there. A very special error correction. So my conclusion is, again, no hype. When you go down to one particular problem, the classical algorithms are great. They are very difficult to improve upon that. So it's very dangerous to claim that we can go to the supply chain or we can go to finance and get an advantage of that. So when you do it, you see that it's only when you have very genuine new ideas, quantum ideas, that there is space for improvement. So I do think that we need to do a lot of work on basic theorems. I still think that there is a fundamental problem, which is how to upload classical data. Imagine that you have a clever algorithm, but you have a data which is exponentially large, the classical data. How do you put that in the quantum register? It must be said that there is no theorem forbidding that. And I use an example that Seth Lloyd uses very often. Imagine I have a lot of data, a picture on a DVD. Well, DVD are, little mirrors that focus in one direction or in the other. So can I shine it with a laser and bounce back the photon into a layer of receptors? And therefore, in one go, I've uploaded the classical data in a quantum state. So there is no abstraction for that, but I've not seen any theorem myself, any experiment where there is a massive upload of classical data in a controlled way. I have not seen that. Definitely there are big advantages. The large space exploration, what I said, that multi-qubits will be a feature map, which is amazing, and the saving of energy. So I do think that as we go ahead, we will be this idea coming more often. I have not presented any of our other work, but we have worked a lot trying to understand crypto primitives, hash functions, many of the protocols which are now in the post-quantum world. We have a team that is addressing this issue. And in that, some of them, like inverting a hash, at some point, with some kind of future computer, quantum computer, I don't know whether we will solve that because it's very tough. We only have a square root of n solution nowadays, a Prof solution. But let me say that the hash functions are structured. We know how a cha-cha algorithm works. There are pieces of it. So we have a structure. We don't know how to use it. What is definitely true is that we would be saving energy if we attack the problem with a quantum computer. So a lot of fairness is needed. And my last transparency is about our effort at TII to make a sort of quantum Linux, an open source language that in a way competes against Qubit and Cirque. It's very efficient. We have really terrific people. Stefano Carrazza is the leader, and it's a full stack. So by now, Kibo is the name of our strategy not only has a language, but it has libraries of solutions. And now when executing the code has to be done, it can be done on classical hardware, on simulation, on CPUs, on GPUs, and on multi-GPUs. Everything is there now and very, very efficient. And on quantum hardware, and I'm also very happy that by now, Kibo is controlling the experiment of Icarus 2 at the lab of Rainer Dunke, and also will be controlling Icarus 10. So that means that it has an scheduler, it has all the sentences for calibration, it has the libraries translating, the high-level abstractions into the pulses, everything is there. It will be controlling an ion trap, the one of Manas, and very likely we will also have something about controlling experiments of high energy physics, in particular how transmons are now used as detectors for sensing, not for computing. And that's it. Thank you very much for your attention.
So thank you very much from our side for this great contribution and this great final keynote presentation. I give the presentation to the audience for questions and comments. And maybe you allow me to start. So I heard your word of caution about the hype, and I see it the same way. So do you think there's something that we should take care of, talking to politicians, talking to funding agencies, that this unrealistic part of the hype is not taking over?
Well, I think that we should have a common commitment, okay? Because these conversations are always face-to-face, one-to-one, and nobody's there to control. So it's simply that I think people should understand that we will all get damage if we don't keep a very high ethical attitude, I think, okay? So I can only speak for myself, but I've been in many talks of colleagues that I simply disagree on the way they present the field. I completely disagree. I think it's completely hyped, and this is not fair. In particular, when they talk to audiences which are not scientists, okay? But when they talk to officers that, the people that give us money. So it's very tantalizing to make such promises, but I'm sorry because it sounds so negative, but I do think that we have to be careful.
So there's Luigi, who has a comment or a question.
Yes, I have a couple of questions. Basically, I have scientific questions, not political ones. I mean, José Ignacio, of course, we talk about politics many times. I think there is a nice work comparison between quantum mechanics, let me say, and nonlinear neural networks. In the past, I'm not really the most expert in that. Maybe Leandro knows more than that, especially in quantum foundations. They try to emulate the quantum mechanics with nonlinear process. I'm not sure to what extent this can be done. So how far they went, basically. The question then is, can you say anything on this interplay between nonlinearity and quantum mechanics with your results?
Well, you see, the point is that the neural network that could contemplate all the superpositions that the circuit does would need an exponential amount of data in each layer. Okay, this is where you see that quantum computers have an advantage, okay? Because it's only a polynomial number of qubits that handle an exponential number of parameters, which the neural network would combine, okay? So in a way, let me go down a lot. Everything is about processing information. Everything is about that. The neural network is a fantastic tool, okay? All these deep neural network, all these natural language processing efforts are amazing, okay? All these BERT algorithms, they're impressive, okay? Now, what's the difference then between a quantum computer? Quantum computer does the same thing. It does the same thing. I give you an example of a classification problem. That's a problem. You can do it with a classical machine or with a quantum machine. The quantum machine only needed 1 qubit and several gates because the superposition is a very clever thing to manipulate there. The classical computer needed intermediate neurons, okay? But they are equivalent at this point. Now, imagine you need a lot of intermediate combinations, a lot. Think of image processing in your eye. What you do is you have convolutional ideas. No, you do first, you detect the lines, the corners, you combine. The next layer say if there are corners and there are 4, that's a square. And the next layer says, and the next layer says, and the next layer keeps saying things. Okay, so the processing, which is stacked, it's in the neural network is there. So imagine that at some point you need an intermediate layer which has an enormous amount of data there. This is where the quantum computer does that in a very efficient way because they have an exponential space. So all this is clear. It's in our minds. It is clear that the quantum computer produces feature maps, which are amazing. What I'm simply saying is that we should go little by little and make theorems about that. We should be clear what is the advantage. And it's very peculiar, but you know, we don't have any theorem about D-wave. We don't have any, absolutely none. And yet people believe that we have a fantastic quantum computer. Really? Really? Does it, as I said, there is the issue whether it's even handling the sign problem. If not, I can simulate efficiently D-wave. I can simulate the physics that is sustaining D-wave. So we have to go to the heart of the issue of each problem to understand what is at stake, and then exploit quantum mechanics to solve that problem, I think. So the kind of talk that Leandro gave, I think it's essential. We need these new ways, for instance, how you make functions of Hamiltonians, how you make the functions of the eigenvalues of the singular value decomposition, how we have to learn to do all these things till we understand finally in clear examples the power of your quantum computer. I think then we will be able to go to this hyped world and now address problems and obtain good results. Okay.
So Luigi, we might continue if you have additional questions.
Another, I want to, so okay, I can ask another question, a little bit more technical. So VQE, okay, so is of course, as we know, it's strongly based on, so you have an Hamiltonian and it works if you can map the Hamiltonian, okay, represent the Hamiltonian using qubits, right?
Yeah.
Say in 1D, at least we have the hope that we can do this reduction, this representation. Then assume you have Hubbard model 2 dimensions. Okay.
Yeah.
So
the best would be to have a quantum computer whose geometry is adapted to the problem. So that's why you know it's very natural to consider quantum computers that have a square geometry. Okay, because then the mapping is much natural, in particular for condensed matter. Okay.
Yeah, but say in two dimensions, you don't have this Jordan-Wigner transformation. So you have to order somehow. You have complicated thing. I simply don't know. So can you map a Hubbard model in a set of kind of interacting crazy interacting qubits and then applying VQE?
Yes. Yes. Oh. Maybe non-efficient, but yes. It's completely different. Jordan-Wigner is dictating to you what is the secret that solves the problem. That we did with Ignacio Latorre. You know, we took the Jordan-Wigner transformation and the Bogolubov and the Fourier transform, the 3 pieces of the solution of these models, and we made the secret that does that. Because you have the theoretical understanding, it's an integrable model, then you can apply these gates and it solves it exactly. Now, can you do it variationally? Of course you can do it. I gave you the examples of the Ising model that were done variationally with no knowledge of the of these things. Would it serve to have a Fourier transform as a pre-processing in the quantum circuit? Very likely, okay, because you have translational symmetry. But can you address these problems with a quantum computer, map them there and address them variationally? Yes. Will it take an enormous effort to train them? Well, if you read a little bit of the literature, there are plenty of papers about training variational quantum eigensolvers, because there is the so-called, well, you know, you may encounter a space full of local minima, and then you don't find the right solution, okay? Imagine a gauge theory where you have amazing degeneration of minima and non-gauge invariant, and therefore the properties you get there are completely wrong, okay? So you have to be very, very careful. This idea that the landscape is subtle and you maybe get trapped is often called barren plateaus. So that means that if you use for training a method of based on gradients, you never find the minima. You keep hovering over the space. Now, we know that since the 70s, you know, when the computers came, we learned about critical slowing down and many other things. And we found problems, collective changes, collective training of parameters. And now people are publishing, they are re-understanding the solutions of the past in classical computation. They are trying to adapt that to quantum computers in the variational setup. So I think it's a matter of time that we get a clear understanding of these things.
Okay, thank you, thank you. So Leandro, excuse me.
Thank you.
Thank you very much. Thank you very much, José Ignacio, for the beautiful talk. Really, thanks. You know, I like a lot your work on these singular value decomposers. I really like that word. That word is really beautiful. So I wanted to ask you a technical question. Like, so there, essentially, you obtain the singular values and the eigenvectors, right, in the Schmidt decomposition of a bipartite state. And then, as you know, you can take a pure state, and you know, by sequential singular value decomposition, you can express it as a matrix product state. And so, in the end, it's kind of tomographic what you're doing, right? Yeah. You get a state, and then you run your variational algorithm, and you obtain the singular values, right? And the Schmidt decomposition. So, have you guys thought of adapting that to some sequential version in which you get like somehow you extract the some matrix some MPS representation of an unknown state?
You're correct. I could take now each of Alice and Bob's states. No, I could do the U dagger on the 0, 0, 0 on the basis, and then I would have the state. And then I could reapply my singular value decomposition, and then I would have a concatenation sequential. And all the unitaries I'm getting very likely finally can be mapped to a tensor network. So it would be a way to construct a tensor network with physical
to learn it,
manipulation.
To learn it, yeah,
yeah,
tomography.
I completely agree with you.
Okay, that's an interesting prospect.
Yeah.
Thank you very much. Thank you again for the talk.
Thank you, Leandro.